Hello everybody, I hope you're all having a wonderful day or night, whatever time it happens to be, wherever you are in the world. My name is Jay, and welcome to episode 2 of History's Hangnails, a podcast where we deep dive on bizarre events and mysteries from our past. Before I begin, something to note. While the first episode was more linear with its dates and events, the information gathered for this one was arranged in such a way that we will be jumping back and forth in time quite a bit in order to maintain the grouping of relevant information. Today's episode takes us back to 1908. On June 30, cited as June 17 before the implementation of the Soviet calendar, at around 7:13 a.m. local time, Evenki natives and Russian settlers in the hills northwest of Lake Baikal observed a bluish light, nearly as bright as the sun, moving across the sky and leaving a thin trail. On the horizon, they saw a flash, which produced a billowing cloud, followed by a pillar of fire that cast a red light on the landscape. The pillar split in two and faded, turning to black. About 10 minutes later, there was a sound similar to artillery fire. Eyewitnesses closer to the explosion reported that the source of the sound moved from the east to the north of them. The sounds were accompanied by a massive shockwave that knocked people off their feet and broke windows hundreds of kilometers away. The explosion registered at seismic stations across Eurasia, and airwaves from the blast were detected in Germany, Denmark, Croatia, and the United Kingdom, and as far away as Washington, D.C. and what was then known as Batavia in the Dutch East Indies. It was estimated that, in some places, the resulting shockwave was equivalent to an earthquake, measuring 5.0 on the Richter scale. Over the next few days, the night skies in Asia and Europe were aglow, and there are reports of brightly lit photographs being successfully taken at midnight in Sweden and Scotland without the use of a flash or bulb. It has been hypothesized that this sustained glowing effect was due to light passing through high-altitude ice particles that had formed at extremely low temperatures as a result of the explosion, a phenomenon that, decades later, was reproduced by space shuttles. In the United States, a Smithsonian Astrophysical Observatory program at the Mount Wilson Observatory in California observed a months-long decrease in atmospheric transparency consistent with an increase in suspended dust particles. Though the region of Siberia in which the explosion occurred was very sparsely populated in 1908, there are accounts of the event from eyewitnesses who were in the surrounding area at the time, and regional newspapers reported the event shortly after it occurred. The first testimony, from one S. Semenov, was recorded by Russian mineralogist Leonid Kulik in 1930. At breakfast time, I was sitting by the house at Vanavara trading post, approximately 65 kilometers south of the explosion. I suddenly saw that directly to the north, over Onkul's Tunguska Road, the sky split in two, and fire appeared high and wide over the forest, about 50 degrees up. The split in the sky grew larger, and the entire northern side was covered with fire. At that moment, I became so hot that I couldn't bear it, as if my shirt was on fire. From the northern side, where the first was, came strong heat. I wanted to tear off my shirt and throw it down, but then the sky shut closed, and a strong thump sounded, and I was thrown a few meters. I lost my senses for a moment, but then my wife ran out and led me to the house. After that, such noise came, as if rocks were falling or cannons were firing. The earth shook, and when I was on the ground, I pressed my head down, fearing rocks would smash it. When the sky opened up, hot wind raced between the houses like from cannons, which left traces in the ground like pathways, and it damaged some crops. Later we saw that many windows were shattered, and in the barn, a part of the iron lock snapped. Another eyewitness source here, by Chuchen of the Shanyagir tribe, was recorded by I.M. Suslov in 1926. We had a hut by the river with my brother Chakaran. We were sleeping. Suddenly, we both woke up at the same time. Somebody shoved us. We heard whistling and felt strong wind. Chakaran said, "Can you hear all those birds flying overhead?" We were both in the hut, couldn't see what was going on outside. Suddenly, I got shoved again. This time, so hard I fell into the fire. I got scared. Chakaran got scared too. We started crying out for father, mother, brother, but no one answered. There was noise beyond the hut. We could hear trees falling down. Chakaran and I got out of our sleeping bags and wanted to run out, but then the thunder struck. This was the first thunder. The earth began to move and rock. Wind hit our hut and knocked it over. My body was pushed down by sticks, but my head was in the clear. Then I saw a wonder. Trees were falling. The branches were on fire. It became mighty bright. How can I say this? As if there was a second sun. My eyes were hurting. I even closed them. It was like what the Russians call lightning. And immediately, there was a loud thunderclap. This was the second thunder. The morning was sunny. There were no clouds. Our sun was shining brightly as usual. And suddenly, there came a second one. Chakaran and I had some difficulty getting out from under the remains of our hut. Then we saw that above, but in a different place, there was another flash, and loud thunder came. This was the third thunderstrike. Wind came again, knocked us off our feet, struck against the fallen trees. We looked at the fallen trees, watched the treetops get snapped off, watched the fires. Suddenly, Chakaran yelled, "Look up," and pointed with his hand. I looked there and saw another flash, and it made another thunder, but the noise was less than before. This was the fourth strike, like normal thunder. Now I remember well, there was also one more thunderstrike, but it was small, and somewhere far away, where the sun goes to sleep. Since the event, there have been an estimated 1,000 papers published about the Tunguska explosion. Owing to the remoteness of the site and the limited instrumentation available at the time of the event, modern scientific interpretations of its cause and magnitude have relied chiefly on damage assessments and geological studies conducted many years after the event. Estimates of the energy produced have ranged anywhere between 13 and 126 petajoules. 1 petajoule equaling 1 quadrillion joules of energy. This is the equivalent of between 3 and 30 megatons of TNT. It was not until more than a decade after the event that any scientific analysis of the region took place, in part due to the isolation of the area and the significant political turmoil affecting Russia in the early 1900s. In 1921, Leonid Kulik led a team to the Podkamenya Tunguska River Basin to conduct a survey for the Soviet Academy of Sciences. Although they hadn't been to the central blast area, the many local accounts of the event led Kulik to believe that the explosion had been caused by a giant meteorite impact. Upon returning, he persuaded the Soviet government to fund an expedition to the suspected impact zone based on the prospect of salvaging meteoric iron. Kulik led a scientific expedition to the Tunguska blast site in 1927. He hired local Evenki hunters to guide his team to the center of the blast area, where they expected to find an impact crater. To their surprise, there was no crater to be found. Instead, there was a zone approximately 8 kilometers across where the trees were scorched and devoid of branches, but still standing upright. Trees more distant from the center had been partly scorched and knocked down, pointing outwards, creating a large radial pattern of downed trees. In the 1960s, it was established that the zone of leveled forest occupied an area of 1,150 kilometers squared, its shape resembling a gigantic butterfly with its wings spread. During the following decade, there were 3 more expeditions to the area. Kulik found several dozens of little bogs, each 10 to 50 meters in diameter, that he thought could be meteoric craters. After a laborious exercise in draining one of these bogs, the so-called Suslov's crater, approximately 32 meters in diameter, he found an old tree stump on the bottom, ruling out the possibility that it had been caused by the strike. In 1938, Kulik arranged for an aerial photographic survey of the area, covering the central part of the leveled forest, about 250 square kilometers in size. The original negatives of these photographs were burned in 1975 by order of Yevgeny Krinov, the chairman of the Committee on Meteorites of the USSR Academy of Sciences at the time, as part of an initiative to dispose of flammable nitrate film. Positive prints were preserved for further study in the Russian city of Tomsk. Expeditions sent to the area during the 1950s and 1960s found microscopic silicate and magnetite spheres in siftings of the soil. Silicates being any member of a family of polyatomic negatively charged ions consisting of silicon and oxygen, and magnetite, a mineral, one of the main iron ores, one of the oxides of iron, which is also ferromagnetic, meaning it is attracted to magnets and can be magnetized itself. Similar spheres were predicted to exist in the felled trees, although they could not be detected by contemporary means. Later expeditions did identify such spheres in the resin of the trees. Chemical analysis showed that the spheres contained high proportions of nickel relative to iron, which is also found in meteorites, leading to the conclusion that they were of extraterrestrial origin. The concentration of the spheres in different regions of the soil was also found to be consistent with the expected distribution of debris from a meteoroid airburst, an event in which a meteor explodes after entering a planetary body's atmosphere. Later studies of these spheres found unusual ratios of numerous other metals relative to the surrounding environment, which was taken as further evidence of their extraterrestrial origin. Analysis of peat bogs from the area, wetlands that accumulate peat as a deposit of dead plant materials, often mosses, also revealed numerous anomalies considered consistent with an impact event. The isotopic signatures of carbon, hydrogen, and nitrogen at the layer of the bogs corresponding to 1908 were found to be inconsistent with the isotopic ratios measured in the adjacent layers, and this abnormality was not found in bogs located outside the area. The region of the bogs showing these anomalous signatures also contained an unusually high proportion of iridium, a very hard, brittle, silvery white transition metal of the platinum group, and the second most dense naturally occurring metal. These unusual proportions are believed to result from debris from the falling body that deposited in the bogs. The nitrogen is believed to have been deposited as acid rain, a suspected fallout from the explosion. As mentioned earlier, there are, of course, many different papers within the scientific community that reported on this event, and they often disagree with each other on the specifics of the chemical analyses. Researcher John Afinaganov has suggested a boulder found at the event site, known as John's Stone, is a remnant of the meteorite, but oxygen isotope analysis of the quartzite, a hard, non-foliated metamorphic rock formed originally from pure quartz sandstone through heating and pressure related to tectonic compression, suggests that it is of hydrothermal origin, and probably formed by magmatism of the Permian-Triassic Serbian traps. This refers to a large region of volcanic rock known as a large igneous province, appearing when magma travels through the crust towards the surface, and is known as the cause of the Permian-Triassic extinction event, approximately 251.9 million years ago. In 2013, a team of researchers published the results of an analysis of microsamples from a peat bog near the center of the affected area, which show fragments that may be of extraterrestrial origin, once again backing up previous results. The cause of this bizarre event is thankfully less of a mystery than one might expect with a topic such as this. The leading scientific explanation for the explosion is, of course, the meteor airburst by an asteroid approximately 6 to 10 kilometers above the Earth's surface. Meteoroids enter Earth's atmosphere from outer space every day, traveling at a speed of at least 11 kilometers a second. The heat generated by compression of air in front of the body as it travels through the atmosphere is immense, and most meteoroids burn up or explode before they reach the ground. More recent calculations included the effect of the object's momentum and found that more of the energy was focused downward than would be the case with a nuclear explosion, and estimate that the air burst had an energy range from 3 to 5 megatons of TNT. A 2019 paper suggested the explosive power of the Tunguska event to have been approximately 20 to 30 megatons. Since the second half of the 20th century, close monitoring of Earth's atmosphere through infrasound and satellite observation has shown that asteroid airbursts with energies comparable to those of nuclear weapons routinely occur, although Tunguska-sized events to the order of 5 to 15 megatons are much rarer. Eugene Shoemaker, an American geologist and discoverer of comet Shoemaker-Levy 9, estimated that 20 kiloton events occur annually, and that Tunguska-sized events occur about once every 300 years. Other estimates place Tunguska-sized events at about once every 1,000 years, with 5 kiloton airbursts averaging about once per year. For reference, a 1 kiloton explosion is equal to 1,000 tons of TNT and is large enough to destroy much of a city block. Most of these airbursts are thought to be caused by asteroid impactors, as opposed to mechanically weaker cometary materials, based on their typical penetration depths into the Earth's atmosphere before exploding. The largest asteroid airburst to be observed with modern instrumentation was the Chelyabinsk meteor, which entered the Earth's atmosphere over the southern Ural region in Russia on February 15, 2013. The meteor itself was approximately 18 meters in diameter, weighing around 9,100 tons, and entered the atmosphere at a shallow angle, finally exploding in a meteor airburst over Chelyabinsk Oblast, about 29.7 kilometers above the surface of the Earth. The light from this meteor was brighter than the sun and visible as far as 100 kilometers away. Some witnesses also reported feeling intense heat from the object. Most of the object's energy was absorbed by the atmosphere, creating a large shockwave, shattering windows, and producing a number of small meteorites. Prior to atmospheric impact, its total kinetic energy was equivalent to the blast yield of 400 to 500 kilotons of TNT. This was 26 to 33 times as much energy as that released from the atomic bomb detonated at Hiroshima. In 2020, a group of Russian scientists used a range of computer models to calculate the passage of asteroids with diameters of 200, 100, and 50 meters respectively, at oblique angles across Earth's atmosphere. They used a range of assumptions about the object's composition as if it was made up of iron, rock, or ice. The model which most closely matched the observed event was an iron asteroid up to 200 meters in diameter, traveling at 11.2 kilometers a second, which glanced off the Earth's atmosphere and returned to solar orbit, as opposed to penetrating and exploding in atmosphere. In regards to the blast pattern, the effect on the trees near the center of the explosion was similar to the effects of Operation Blowdown, an explosives test carried out in the jungle of Cape York Peninsula in 1963 by the Australian Army to simulate the effects of a nuclear weapon on tropical rainforest. These effects are caused by the blast wave produced by large airburst explosions. The trees directly below the explosion are stripped as the blast wave moves vertically downward, but remain standing upright, while trees farther away are knocked over because the blast wave is traveling more horizontal when it reaches them. Soviet experiments performed in the mid-1960s with model forests made of matches on wire stakes and small explosive charges slid downward on wires produced butterfly-shaped blast patterns similar to that found at the site. The experiment suggested that the object had approached at an angle of roughly 30 degrees from the ground and 115 degrees from the north, and had exploded in mid-air. In 1930, the British meteorologist and mathematician F.J.W. Whipple suggested that the Tunguska body was a small comet. a comet is composed of dust and volatiles, such as frozen water and gases, and could have been completely vaporized by the impact with Earth's atmosphere, leaving no obvious traces. The comet hypothesis was further supported by the glowing skies observed across Eurasia for several evenings after the impact, possibly explained by dust and ice that had been dispersed from the comet's tail across the upper atmosphere. By the 1960s, this idea had gained general acceptance among Soviet Tunguska investigators. In 1978, Slovak astronomer Libor Kresak suggested that the body was a fragment of comet Encke. It is also responsible for the Beta Taurids, an annual meteor shower which is at maximum activity around June 28 to 29. The Tunguska event coincided with the peak activity of that shower, and the approximate trajectory of the Tunguska object is consistent with what would be expected from a fragment of comet Encke. It is now known that bodies of this kind explode at frequent intervals, tens to hundreds of kilometers above the ground, and military satellites have been observing these explosions for decades. During 2019, astronomers searched for hypothesized asteroids around 100 meters in diameter from the Taurid swarm between July 5 to 11 and July 21 to August 10. As of February 2020, there were no reports of any such discoveries. The next hypothesis comes from astronomer Zdeněk Sekanina in 1983, who published a paper criticizing the comet hypothesis. He pointed out that a body composed of cometary material traveling through the atmosphere along such a shallow trajectory ought to have disintegrated, whereas the Tunguska body apparently remained intact into the lower atmosphere. He also argued that the evidence pointed to a dense, rocky object, probably originating from an asteroid. This idea was further boosted in 2001, when a study was released calculating the probabilities based on orbital modeling extracted from the atmospheric trajectories of the Tunguska object. They concluded with a probability of 83% that the object moved on an asteroidal path originating from the asteroid belt, a torus-shaped region in our solar system centered on the Sun and spanning roughly the space between the orbits of the planets Jupiter and Mars, rather than a cometary path. Proponents of the comet hypothesis have also suggested that the object may have been an extinct comet, having expelled most of its volatile ice, with a stony mantle that allowed it to penetrate the atmosphere. The main issue with the asteroid hypothesis is that a stony object should have produced a larger crater where it struck the ground, but no such crater has been found. It has been posited that the passage of the asteroid through the atmosphere caused pressures and temperatures to build to a point where the asteroid abruptly disintegrated in a massive explosion. The destruction would have to have been so complete that no substantial remnants survived, and the material scattered into the upper atmosphere during the blast would have caused the sky to glow as it did. Models published in 1993 suggested the object would have been about 60 meters across, with physical properties somewhere between an ordinary non-metal meteorite or chondrite and a carbonaceous chondrite, comprised of many grouped and ungrouped meteorites and containing some of the most primitive known meteorite groups. Christopher F. Scheiber, an American astrobiologist, proposed a process whereby a stony meteorite could have exhibited the behavior of the Tunguska impactor. The models showed that when the forces opposing a body's descent became greater than the cohesive force holding it together, it blew apart, releasing nearly all of its energy at once. This would result in no crater being formed, with the damage resulting from the thermal energy released in the blast being distributed over a fairly wide radius. Three-dimensional numerical modeling of the Tunguska impact done by S.V. Utyuznikov and D.V. Rudenko in 2008 supports the comet hypothesis. According to their results, the comet matter dispersed in the atmosphere, while the destruction of the forest was caused by the shockwave. During the 1990s, Italian researchers, coordinated by physicist Giuseppe Longo from the University of Bologna, extracted resin from the core of the trees in the area of impact to examine trapped particles that were present during the 1908 event. They found high levels of material commonly found in rocky asteroids and rarely found in comets. In 2009, it was contended that the impact was caused by a comet because of the sightings of noctilucent clouds, glowing cloud-like phenomena in the upper atmosphere of Earth following the impact, caused by massive amounts of atmospheric water vapor. The same year, a team of Russian researchers led by Edward Drobyshevsky have suggested that the near-Earth asteroid 2005 NB56 may be a possible candidate for the parent body of the Tunguska object, as the asteroid had made a close approach to Earth just 3 days before the impact. The distance of this approach being reported as 0.0645 AU, or astronomical units, a unit of length effectively equal to the average or mean distance between Earth and the Sun. For reference, one astronomical unit is equivalent to 149,597,870.7 kilometers. The team suspected that 2005 NB56's orbit likely fits with the modeled orbit of the Tunguska object, even with the effects of weak gravitational forces. In 2013, analysis of fragments from the Tunguska site by a joint US-European team was consistent with an iron meteorite. The February 2013 Chelyabinsk event provided ample data for scientists to create new models for the Tunguska event. Researchers used data from both events to perform a statistical study of over 50 million combinations of bolide, an exceptionally bright meteor, though it may also refer to any large crater-forming body or to one that explodes in the atmosphere. These tests were able to reproduce the Tunguska scale damage when breaking apart or exploding at similar altitudes. Some models focused on combinations of properties which created scenarios with similar effects to the tree fall pattern, as well as the atmospheric and seismic pressure waves of Tunguska. 4 different computer models produced similar results, concluding that the likeliest candidate for the Tunguska impactor was a stony body between 50 and 80 meters in diameter, entering the atmosphere at roughly 55,000 kilometers an hour, exploding at 10 to 14 kilometers above the surface of the Earth, and releasing an explosive energy equivalent to somewhere between 10 and 30 megatons. This is similar to the blast energy of the 1980 volcanic eruption of Mount St. Helens. Thankfully, the research team also concluded that impactors of this size hit the Earth at only an average interval scale of millennia. In 2007, scientists from the University of Bologna identified a small bowl-shaped lake named Lake Checo, approximately 8 kilometers north-northwest of the center of the main impact. They do not dispute that the Tunguska body exploded in mid-air, but believe that a 10-meter fragment may have survived the explosion and struck the ground, though this hypothesis has been disputed by other impact crater specialists. A 1961 investigation had dismissed a modern origin of Lake Checo, saying that the presence of meters-thick silt deposits at the lake's bed suggest an age of at least 5,000 years, but more recent research suggests that only a meter or so of the sediment layer on the lake bed is normal sedimentation and of a depth consistent with an age of about 100 years. Acoustic echo soundings of the lake floor also provide support for the hypothesis that the lake was formed by the Tunguska event. They revealed a conical shape for the lakebed, which is consistent with an impact crater, and magnetic readings indicate a possible meter-sized chunk of rock below the lake's deepest point that may be a fragment of the colliding body. Finally, the lake's long axis points to the center of the Tunguska explosion, about 7 kilometers away. Work is still being done at Lake Checo to determine its origins. In 2017, new research by Russian scientists pointed to a rejection of the hypothesis that Lake Checo was created by the Tunguska event. They used soil research to determine that the lake is at least 280 years old, clearly having existed prior to the Tunguska event. Future soil analyses conducted also supported these findings. Another issue lies in the physics of these claims. It is unlikely that a stony meteorite in the right size range would have the mechanical strength necessary to survive atmospheric passage intact, and yet still retain a velocity large enough to leave a crater that size upon reaching the ground. Though scientific consensus is that the Tunguska explosion was caused by the impact of a small asteroid, there will always be some dissenters. astrophysicist Wolfgang Kund has proposed that the Tunguska event was caused by the release and subsequent explosion of 10 million tons of natural gas from within the Earth's crust. The basic idea is that natural gas leaked out of the crust, then rose to its equal density height in the atmosphere, drifted downwind in a sort of wick, and eventually found an ignition source such as lightning. Once the gas was ignited, the fire streaked along the wick, then down to the source of the leak in the ground, causing the explosion. Geophysical mechanism has also been posited as a likely cause. The intense explosion caused by the Tunguska event flattened an estimated 80 million trees over what is now known to be an area of 2,150 kilometers squared, and eyewitness reports suggest that at least 3 people may have died in the event, a figure that is neither confirmed nor all that terrible in the scheme of outcomes that might have been. Don't forget, I stream 4 days a week over at twitch.tv/Jabberwocky. You can also show your support and help out the podcast by heading to patreon.com/Jabberwocky and signing up for one of the 3 member tiers listed. Make sure to keep a weather eye out for announcements regarding future episodes. @HangnailPod is the official Twitter for the podcast, and all announcements will appear there. Thank you all for joining me. I hope you enjoyed the episode, and I'll see you next time.